Hello everyone, in this video we'll talk about generative adversarial networks and more in particular about its application to the generation of X-ray CT images of a partially saturated sand. So this is my work during my time as an assistant professor in Zhejiang University in China. And first of all I will introduce what a GAN is. So we can look at this figure here. A GAN is an adversarial training method for a generative model in which we want the generator to learn to reproduce synthetic images that match the images from a database. Actually, generative adversarial networks can be applied to other kind of data like waveforms, audio, or language models like ChatGPT, for instance. So the idea is that we have a database of real samples. Those are images that in this case come from an X-ray CT of a partially saturated sand. This is a material that is of interest for the oil companies because you want to study it in the sense that you want to know its mechanical properties, permeability, and you need to be able to make cuts of it, to see the inside. So that's why X-ray CT allows us to have a 3D image of this kind of material. Okay, so we have these samples that in this case are cuts of this 3D CT image. And we have a database of it, like 500 or 1000 or 2000 of these images. And we want a generator to learn its underlying properties or features and then generate images that are synthetic but have the same properties of the real images. Why we would like to generate synthetic images if it's not to cheat or to do something illegal? Well, because getting these images is expensive in the sense that running a CT image machine requires time and money. So sometimes the quantity of images that you have available are limited, and in machine learning or fitting techniques, you want as much data as possible to increase the accuracy of your predictions. So that's why it may be interesting to use a generative adversarial network to increase the data you have in your database to train predictive models. So this is called data augmentation. Okay, so what we will do is to take our real samples and then generate a series of fake samples using a generator. Then we group this by batches. So let's say here there are three real samples, 3 fake samples, and we feed these 6 images to a discriminator. So these are 2 groups of 3. And the discriminator needs to tell which is fake, which is real. So the discriminator doesn't know which comes from the generator, which comes from the database, and needs to give a score either if it believes that they are real or fake. Both generator and discriminator are penalized when they make a mistake. So a mistake for the discriminator would be considering a fake image real or considering a real image fake, while for the generator a mistake would be to not being able to fool the discriminator. So this continues in an adversarial game. The weights and biases of the generator and discriminator, which are neural networks, are updated according to these penalties. And theoretically this converges to nice equilibrium. And at this point we have a generator that is very good, hopefully, to generate images that have the same features as the real images. And the discriminator, we can dismiss it, but actually we could also use it to try to catch fake images. Like imagine in ChatGPT, now you have many students that use ChatGPT to create fake reports for the high school or something like that. So you could use the discriminator that has been used to train something like ChatGPT, although I'm not expert in large language models. You could use it instead of discarding it just to catch cheaters that use it for fraudulent applications. Okay, that's what a GAN is. And this is how it's used to generate fake videos, fake faces of people, celebrities, nudes, something like that. But this is a scientific application. So we said that our material has some interest in the oil industry. We will focus on permeability. So this is a partially saturated sand. So this is sand which has a part of the void filled by water and part of it filled by gas. So in the case we want to extract the methane gas from this medium, you are interested in the permeability through the pores of this medium filled by gas, because the water is blocking the flow of gas. So that's a physical property. It's not enough for you that this GAN makes images that look like the real images. We want to make sure that the images have the physical properties that we are looking for. So then we can make predictions on these physical properties with the synthetic images. Okay, these are the equations for the loss function for this adversarial game. We will not spend too much time on this. So what to do to force this adversarial game to go towards a nice equilibrium that makes the images look like the real images, but in addition they also have the physical properties that are correct, or in other words, that cannot be distinguished from the real physical properties, statistically speaking. So what we do is to enrich the model with what we call an informed discriminator, which is a discriminator that works in parallel to the neural network discriminator. And this has information about physics, and we will discuss later which kind of physics or information. This discriminator will evaluate also real samples side by side to fake samples and give a score, and this score will be used to update the generator with errors and gradients, which allows the generator to learn what is a good and what is a bad generation, but not only according to features that generator found in the image database, but now also knows about physics. For the moment, just believe me, what is inside this red box is physics, although we'll see that this is actually a surrogate. Okay, maybe we'll jump back for a second. So I was talking about permeability through porous media, because this is what is of interest for this material for the oil industry to compute well productivity in gas extraction, etc. But you know, if you are an engineer or you study physics or mathematics, that computing permeability from porous media, knowing the granulometry or the geometry of its grains and its saturation, is not easy. You need to solve a PDE, which requires something like finite element equations, which is expensive. So if we try to run a finite element model in parallel to our GAN, so imagine this informed discriminator was a finite element model, this will slow down a lot our training process. In addition to train GAN models, depending on the rig you are using, but it may take several days. It's a very time-consuming training process. So we don't want to slow it down by putting in parallel some finite element simulation, which will be the bottleneck for the training process. So what we do is to look for a surrogate, and we found that it has already been proved that we can use the fractal dimension of granular media to make a prediction of its permeability, and this is a very good prediction. And we have numerical methods that allow us to extract the fractal dimension very cheaply, numerically speaking. So that's what we are doing. We are assuming that fractal dimension is a good surrogate of permeability. We compute fractal metrics of these images, and then we compute the Wilcoxon rank sum test. Why we do Wilcoxon? It's because the batches we're using are less than more or less 32 images, so we cannot use statistics that assume some kind of distribution. So we don't know the distribution, we cannot assume normality. That's why we use Wilcoxon rank sum test. Okay, and from this we infer some p-values that will be used by the loss function to compute errors and gradients. Okay, actually I will not extend much more on this, but I can tell you that statistics say that this method is better than not using the informed discriminator. So this is better than just this. If we compare the statistical distribution of physical properties, in this case, the surrogate of permeability in the synthetic images. So the conclusion of this at this stage is that this is good. The images that are being created are better in the sense that they cannot be distinguished from the real ones in terms of fractal metrics. Okay, and you can say, why should we care? This is a surrogate. There is no proof that in this application surrogate is actually correlated to actual physics in a way that neither actual physics can be found as being synthetic. So you are right, and the only way to solve this problem is, I will jump all this. The only way to solve this is to run an actual physical problem in which we compute permeability of the synthetic and real images, and we compare those statistically to the real ones. So we can say that if using a surrogate as a physics-informed module in generative adversarial networks serve to produce a physically meaningful image of a partially saturated sun. So we do this, we segment this image, use segmentation in the B in figure 17, and we just separate the grains in white, the gas in black, and the water in gray. We mesh it, and we solve a finite element model. Let me see, what is the equation here? So we are solving this PDE, this partial differential equation. You see that this has the shape of the wave equation, because the coefficients of the second partial derivative with respect to x and y, which are over two spatial dimensions, are both positive. So that has the shape of an ellipse, elliptic PDE. We have a source term, so this is not homogeneous. And we use the term C, which is a bit different than the wave equation, because in the wave equation usually we denote this C square. So C would be the wave propagation velocity in this medium. Here, this is not the wave propagation, because we use this to compute flow velocity profile in viscous flow. We consider that this is viscous because the size of the grain is small enough, so there is no turbulence. And then we impose the boundary conditions. We use this term mostly for stability. It's very small, but we need it for the problem to be numerically stable. And here we have the results. So integrating, in the left you see the meshing of the different fractions. So you have void, you have water, and you have void plus water. In the center figure you see the velocity profile. I repeat, this is a viscous flow. That's why we can obtain it by solving this equation that looks like the wave equation. And by integrating this, we get the discharge, the total flow of water or gas or water plus gas. And by operating this, we can work out the permeability of this section. Okay, so now it's time to compare statistically the permeability from real and generated images. And so the ground truth is the real image, and the reference is the synthetic image that comes from a model which is not supervised by surrogate of permeability, and the others are three different parametrizations of this supervised model. And the conclusion is looking at the p-values, which is a statistic which tells us the likeliness of a distribution to be the one from the model or not. We see that the supervised versions, which are the I-75, K5, K6, and K7, are better than the reference for the three cases: gas, water, and pore permeabilities. Okay, so this was an example of a generative adversarial network. This was my first work on this subject during my time in Zhejiang University. The model is available. You can find it in these links here. So all the model and the data used for validation is fully available. You can download it. It works in MATLAB, and you can try it with a different database of images. That's most of it. So at the moment I'm working with this model applied to medical images. I'm generating images of brains, but I'm not going to talk more about this because it's not yet published, this work. And in the next videos I will talk about other applications of generative adversarial networks, mainly finite element model GAN, which uses a proper finite element model of mechanical properties to assist a generative adversarial network of a 3D image, and another one in which we look at images with more than two phases. So in this case we have a partially saturated sand with a porosity which is partially frozen, so with lengths of ice growing. Okay, thanks for watching. See you in the next video. Bye.